In this video, you're going to learn about Kubernetes CPU. We'll cover what happens when you set a CPU request and a CPU limit for your containers. So Kubernetes has its own abstraction for CPU, so you won't be operating in quotas, periods, and shares. Instead, you'll be giving a concrete CPU value, for example, 1.5 CPUs. You can also specify it in millicores, and for that, 1000 millicores is one core. Under the cover, these are translated in deterministic ways to using CPU shares, CPU quota, and CPU period. Understanding how this works and how to set your requests and limits based on the requirements for your application is a key skill in being successful in deploying Java applications on Kubernetes. If you don't remember about CPU quotas, periods, and shares, now would be a good time to go and review those videos. A CPU request is set per container. So inside our deployment here, inside the containers section, we've said that our server app is only allowed 1.5 CPUs. Or more accurately, we've requested 1.5 CPUs. That means that our pod will only get deployed on a node that has 1.5 nodes free in terms of scheduling, as we described in the last video. All of the examples we've had so far for deployments have had a single container, but the containers under spec in our deployment is an array, so we can put as many containers as we like. If we were to have multiple containers, then our total resources would be the sum of all of the requests. Like we saw in the previous video, CPU requests' primary purpose is for scheduling. Requests make sure that we don't oversubscribe a node. So even if a node has got very limited CPU usage, if it has containers running on it whose requests add up to the total resources of the node, then no more pods will be deployed there. If there's no room on any of the nodes and you've specified a request, then your pod will remain pending and it won't be started. So how are CPU requests implemented under the covers? Well, each CPU, or 1000 millicores, is translated to 1024 CPU shares for the underlying C group. Now, with what you know about CPU shares, then that matches what we want from requests. The Kubernetes scheduler makes sure that if a node has 6 cores, then containers with shares adding up to 6 times 1024 will never be exceeded. This works nicely with how later versions of Java treat CPU shares, because if you remember, Java also treats 1024 CPU shares as a single CPU when calculating the available processors that it returns and bases ergonomics from. The fantastic thing about CPU requests and CPU shares is that if there are free CPU cycles on the box, your containers will be allowed to use them. And assuming that you want to save money and fully utilize your hardware, this is a good thing. Which of course means that CPU shares and thus Kubernetes CPU requests are only enforced when there's contention. When all of the containers on the box want to use as much CPU as they can, then it will fall back to the relative values of each container's CPU shares. So a key takeaway when deciding whether to use CPU requests or CPU limits is that requests are fantastic for node utilization. So you might be wondering, why would I ever not want to use CPU requests? We're about to find out what limits are, and maybe they might seem more appealing. And the reason for that is that the amount of CPU that a container gets to use is dependent on what else is running on the node. And what else is running on the node, and even which node a container is running in, is in constant flux in a Kubernetes cluster. And if you're used to doing traditional capacity planning, load test your application, decide how many servers it needs, the equivalent in a containerized world would be doing some capacity and load testing and then deciding what CPU requests or CPU limits that you might need. But if you happen to do your load testing on a day where the Kubernetes cluster has very low utilization, you might think that your application performs fantastically. You've given it 2 CPUs as the requests, but it's chunking through lots and lots of work. And that is because your Java application might be getting access to hundreds of cores, even though you've only requested 2. This can make this type of traditional planning quite hard and can make you consider using limits. And we'll learn about these next. So CPU limits are an additional configuration we can have for CPU, and you can set both requests and limits, and it's perfectly valid to do so. The difference with CPU limits is they're not used for scheduling. So nodes can be overcommitted for limits. If a node has, say, 3 CPUs, it could have containers on there which have set the limits to vastly more than 3 CPUs, because scheduling uses CPU requests. The purpose of limits is to define a hard limit for how much of a resource your container can use. For that reason, they're implemented with CPU quota. Up until a very recent version of Kubernetes, the CPU period was hard-coded to 100 milliseconds. Then, if you were to set a CPU limit, it would set a CPU quota of the number of cores, or the millicores divided by 1,000, times by 100. So that means that if you requested 1.5 cores, you'd end up with a CPU quota of 150 milliseconds. And with a CPU period of 100 milliseconds, this is kind of like 1.5 cores. But if you remember back to what we learned in the container deep dive section, then a container can use up its quota in a fraction of the period. And this can happen because multi-threaded applications could get to run on many, many cores and use up their 150 milliseconds of CPU time within a few milliseconds, meaning that your application can get throttled and you can end up with latency spikes and really weird runtime behavior. A takeaway of CPU limits is that they pretty much all use a CPU period of 100 milliseconds inside Kubernetes, which means that you can end up with some significant throttling. If you have a much smaller CPU period, say 10 milliseconds, then the most your application can be throttled is for the remainder of the period, which might be 8 milliseconds. But if you have a very large CPU period, like Kubernetes does, of 100 milliseconds, if you use up your quota within 1 or 2 milliseconds, you can be paused for 90 to 100 milliseconds, which is a significant pause if you're building a real-time application. So there is no one answer to whether you should set requests, limits, or both. However, I would say that you should nearly always set requests. If you don't set CPU requests, your pod can be scheduled on any node. And then when the other containers on that node that do have CPU requests need to use the CPU, you're the back of the queue. Your container will not get to use the CPU. So unless it's a background job where you don't mind how long it takes or how much CPU it gets, always set a request. And regarding limits, if you want to limit peak performance or you want the performance to be deterministic, then consider limits, but just beware of the risks of throttling.